So the cardiac cycle, we're going to look at 4 phases. Some textbooks break up into 5. This one has, this diagram shows 5. Your lab manual shows it as 4. We're going to talk about ventricular filling, isovolumetric contraction, ejection, and isovolumetric relaxation. All right, those 4 phases. Basically, we're going to fill the ventricles, we're going to squeeze, we're going to eject the blood out, and we're going to relax. Repeat ad infinitum until death. So you start with number 1, and again, understand what systole and diastole means. Systole is contraction, diastole is relaxation of that tissue, and we're just concerning ourselves with the ventricles right now. When we say systole and diastole without mentioning a chamber, we are talking about ventricles. So it doesn't matter where you start, but most start with the period of isovolumetric contraction. Look at the name, isovolumetric, same volume, but they're contracting. So the ventricles are contracting and building pressure, but no blood is entering or leaving the ventricles. So during both isovolumetric phases, the semilunar valves are closed and the AV valves are closed. Both sets of valves are closed during both isovolumetric phases. All right, so isovolumetric contraction tells you the ventricles are contracting, building up pressure. So this is a very brief phase. It ends when the semilunar valves open, and that starts the period of injection. Blood leaves the ventricles and enters either the pulmonary trunk or the aorta. But the period of ejection is also systole, and that ends when the ventricles stop contracting and begin to relax. The first thing that happens when the ventricles begin to relax is the semilunar valve snaps shut again, and you start the period of isovolumetric relaxation. So continue on from the slide above, isovolumetric relaxation, just like contraction, is a very brief period. All 4 valves are closed and the pressure is quickly reduced in the ventricles instead of contraction where the pressure quickly builds. So eventually the pressure in the ventricles will lower enough to where the ventricular pressure is lower than the atrial pressure, and blood always flows from an area of high pressure to low pressure. So when the ventricle pressure is low enough, the period of isovolumetric relaxation stops when the AV valves open and blood starts to enter the ventricles. So when the AV valves open, you have passive ventricular filling initially, where blood just flows into the ventricles and fills the ventricle as that cavity, as the walls relax and the volume of the ventricle increases. That is basically most of the ventricles filled through passive ventricular filling, and that is kind of topped off by active ventricular filling when the atria contract. But again, most blood flows into the ventricle through passive ventricular filling. So again, ventricular filling, you sometimes see passive versus active broken up, but we'll just know it as ventricular filling. And then as soon as the diastole ends and the ventricles start to contract, systole starts. Again, the very next thing you'll see is the AV valve snap closed, and then the period of isovolumetric contraction starts. And again, circles through these phases. So you should understand these phases and what's going on in the heart. Now, take another look at these phases. Again, this graph varies depending on the textbook that you will look at. So at the top you have the electrical trace, the P, Q, R, S, and T waves. Remember, the P is atrial depolarization and atrial contraction quickly following that. Atrial repolarization or relaxation occurs during the QRS phase, which is showing ventricular polarization, and again ventricular contraction will occur quickly after. So the QRS ventricular repolarization masks the atrial repolarization. You don't ever see that. And then T, the T wave, is ventricular repolarization. So you'll see the relaxation follow the T wave. The next set down, you see our pressures, and the key to that is as follows. The black solid line is the pressure in the left ventricle. The blue dashed line in the bottom is the pressure in the left atrium, and the red dashed line is the pressure in the aorta. So following that down, then the next set of data. I guess the next trace below is the left ventricle volume, and then you have the lub dub, the heart sounds, as they appear with everything else. So we already talked about the electrical trace. So following the next trace down, as you see during the period of isovolumetric contraction, the pressure in the left ventricle, again the black solid line, increases dramatically within a short period of time. So when the pressure in the ventricle eclipses and surpasses the pressure in the aorta, you get the period of injection starting. The semilunar valves open and blood starts to flow into the aorta. Pressure within the ventricle and the aorta are pretty much the same at this very brief period of time while blood is flowing from one to the other. The semilunar valves are open. So during the period of ejection, again, the AV valves are closed, semilunar valves open. Blood is flowing into the aorta, and you look down below on the third trace, the volume of the left ventricle decreases during the period of ejection, which should make sense. If the left ventricle is ejecting that blood into the aorta, the volume that is in the left ventricle is going to decrease. So at the end of the period of ejection, you see the pressure within the ventricle and the aorta both fall when the blood within the ventricle reaches the point of the pressure within the aorta, and it actually eclipses that and goes below that. The blood will kind of start to flow back to the semilunar valves and very quickly cause the semilunar valves to snap shut. And this starts again the period of isovolumetric relaxation, where the ventricles diastolically relax and pressure quickly falls within the left ventricle. You see the pressure within the aorta falls, and then you have what's referred to as the dichroic notch, where you have a quick increase in pressure and then again a kind of a slower decrease. So that increase in pressure when the valve, shortly after the semilunar valve snaps shut, that is a product of the elastic membrane within the aorta. That is the aorta stretching out a little bit and then recoiling back, and that recoil increases that pressure very slightly within the aorta. But again, you get a constant drop of pressure within the aorta as the blood flows away from the aorta into other areas until the next period of ejection. So again, kind of flowing down during the period of isovolumetric relaxation, the pressure in the ventricle decreases until it gets below the pressure in the atria, and that is where the AV valves open up at the end of the period of isovolumetric relaxation. During the ventricular filling phase, again, the pressure in the atria is just slightly above the pressure of the ventricle. But if you look down at the third trace, you see the volume of the ventricle increases during that passive ventricular and active ventricular phase. Again, if you look at the volume during passive as opposed to active, the majority of the volume is reached during passive filling. The atria contracting and finishing off the active ventricular filling really just kind of tops off that ventricle. And again, I haven't mentioned it, but down at the bottom, you see again the lub dub sounds, the heart sounds. Those are caused by, again, the lub at the beginning of the isovolumetric contraction phase is caused by the AV valves closing, and the dub starting at the beginning of the isovolumetric relaxation phase is caused by the semilunar valves closing. So again, the ejection phase is relatively quick. I think lub dub. Between lub and dub, you are ejecting all that blood within the ventricle. So you have lub, ejection, squeezing out, relaxation, dub. And then you have a kind of a longer gap as the ventricle fills. So again, if you look at like the time, it takes a lot longer for the ventricle to fill than it does for the ventricle to eject all that blood. So, understand what it is you're seeing here. Understand what the valves are doing during each phase, which phase the valves are open and which phase the valves are closed, and things of that nature. So you will see a graph or two and some questions about this on the practical. So when you think about the four valves, you can actually selectively listen for those four valves and their motion when you look at in the chest. So when you guys get to nursing and you start positioning your stethoscopes in certain areas, you're looking for to listen to a specific valve. So just kind of keep that in mind. One thing you should know are the location of the pulse points. This is also in your lab manual. There is an exercise where you are supposed to find the pulse points on each other. You should know most of these, if not all. If not for this class, certainly you'll start doing pulses in nursing when you get to each other, get there. But I would like you to know where these pulse points are, where you can find an artery that is relatively close to the surface. And again, look at the name of them. The arteries. The pulse points are named after the artery that they're being taken on. So to take blood pressure with a sphygmomanometer, a blood pressure cuff, the first thing you've got to understand is a turbulent versus laminar blood flow. Laminar blood flow is how blood usually flows in a nice, straight, open blood vessel with no sharp bends. And as you see there, it kind of flows in like layers. The blood vessel itself causes friction, and blood is little particles basically. So the blood right next to the vessel flows the slowest, and you can imagine like layers of blood into the deepest area of the lumen, and that flows the fastest, where you see the longest arrow here. So the blood flows in like layers. The different layers go at different speeds, basically. So a turbulent blood flow, as you see there, there's a constriction or a reduction in diameter, or sometimes a sharp bend within that blood vessel. But you can hear this with either a stethoscope or a Doppler mechanism. It'd be kind of like a whooshing sound, like whoosh, whoosh, whoosh. As the blood moves and as it creates eddies. Imagine being behind a semi-truck on a highway, and what you're feeling is the turbulence, the eddies. And I'm sure it's a lot noisier than if you didn't have that truck in front of you. So understanding that, and that laminar flow is silent, turbulent flow can be heard. So when we take a blood pressure cuff, we wrap it around the arm. What we do is we basically seal off that artery. We're looking at the brachial artery, and we auscultate, we listen, using our stethoscope to that artery just distal to the cuff. So the process is you wrap the cuff around the arm, pump up screw the little valve closed, and you pump up the pressure to usually over 200, well above what you expect the systolic pressure to be. And so what you see there on the very right is kind of a diagram of the artery during both systole and diastole. So when and you see there the blood pressure range there in blue. So when the pressure in the cuff is above blood pressure, it will occlude the artery and keep the artery closed. All right, there will be no sound. So what you do is you open up the little needle valve on the bulb, and you very slowly start to reduce the pressure in the cuff as you listen to the stethoscope. So what happens is when the pressure in the cuff reaches systolic pressure, and you see that at number 2 there, where you see the first sound is heard, when the pressure in the cuff is equal to systolic pressure, during systole, you will get the artery open just ever so slightly, and you'll have some turbulent flow, and you will hear it. So when you're lowering your pressure in the cuff and you hear the first whooshing sound, that is what you report as your systolic pressure. Okay, so your systole is the pressure equal to that in the cuff. So what you'll see is you keep reducing the pressure, you're going to hear more whooshing during systole. All right, and then what you'll eventually see is the pressure in the cuff will be below systolic pressure, and the artery will be completely open during systole and silent during systole, but it will be occluded to some degree during diastole, and you'll still have turbulent flow during diastole. So you'll still hear a whooshing sound. It might sound a little different, come a little different part of the cycle, but when you stop hearing the whooshing sound, that is when your diastolic pressure is then equal to the cuff pressure, and that's what you report as your diastolic pressure. So you report your systolic pressure when you first hear a sound, and when you last hear the sound, that is the pressure you report as your diastolic pressure. And again, what you see in the artery is there. So you're looking at an area where the artery first opens up, and you get turbulent flow from systole, and eventually systole will be completely open, and your blood pressure, cuff pressure will be below the systolic pressure, but it'll still be above the diastolic pressure, and you'll hear some whooshing during diastole. Again, once you stop hearing those sounds, that means that artery is completely open during diastole, and you have no more turbulent flow, and it's all laminar flow, which means the cuff pressure is equal to the diastolic pressure at that point. So again, understand what it is you're looking at when you take a blood pressure from the cuff. So as you look at the fluctuations of pressure, I think this is kind of an important thing to look at with the push of pressures, and where you will see a diastolic and systolic pressure, and where you'll just see a constant pressure. But at the bottom, you see you've got the aorta, arteries, arterioles, capillaries, and then venous veins, vena cava. So basically, as you get farther and farther away from the heart and the smaller and smaller arteries, the fluctuation between systolic pressure and diastolic pressure becomes less and less and less. All right, so the mean pressure, you see the average, it arcs down, and eventually, by the time you get to the capillaries, you don't really have flows of, you have a constant flow of blood. The thing to think about is say you're stationed at part of some area of the aorta. So during your systole, you're going to have blood rush by very, very quickly. And then during diastole, when the ventricle is relaxing and filling, the blood in the aorta is either going to, depending on where you are, stop very briefly, or stop and just kind of get a slow push forward during diastole. Then systole occurs, and you get this rush of blood, and then it slows during diastole. So you get not only a fluctuation of pressure like you see there, but also a fluctuation of flow rates. So there's kind of a changes in flow. And by the time you get to the capillaries, the pressure change is the pressure wave is reduced, and it's just a constant push. So when you get to capillaries, you can look for videos of blood flowing through capillary beds and things like that. It is a constant speed, it's a constant trickle. But if you were to look at like arterial blood, there's a classic Monty Python bit where guys go, "Oh, it's just a flesh wound," but he's spurting out blood. But what you'll see with like arteries and things like that, with each contraction of the heart, you'll get a spurt of blood, and then it'll stop for a second as the ventricle relaxes. Then another spurt of blood, and again, that the spurting of blood is kind of that's your systolic pressure. So you see that wave of pressure with each heartbeat. Again, that whole wave decreases the farther and farther you get from the heart.